Hello, and welcome to part 3 of the protein assignment series. In part 1 and 2, we had covered how to assign your protein using triple resonance experiments and NOSIs, along with strip plots. In this video, we are going to cover additional tools that can assist with the assignment process, and what to do after you are done assigning your protein. The first tool we are going to discuss is Sparta Plus. And you can get Sparta Plus from the site here. It's built into NMR Box. And this is a chemical shift prediction software that predicts the chemical shift of the backbone atoms of a protein. So that being the carbonyl, the amide nitrogen and hydrogen, the alpha carbon and its hydrogen, and the beta carbon. And this is based on the protein structure. And so the only input this program requires is a PDB file. However, if you look here at the directions for using Sparta Plus, you'll note that hydrogens must be present in the PDB file. And in most cases, that means these hydrogens will have to be added. Now, hydrogens can be added a number of different ways. I would personally recommend using a program called Reduce, and that's built into Molprobity. So to use this, you can either upload your own PDB file, or you can fetch it by just putting in the PDB code or ID, and then this will read the PDB file. You click continue. You can click add hydrogens here. There are a number of settings that you can adjust, and then if you click start, it will add the hydrogens using this reduce program, right? And once this is done, now you have your PDB files. Now you can flip some of your amino acids here, and you can click continue, and there's a number of different things you can do. But what we care about is the PDB file that has the hydrogens added. So if you click here where it says added hydrogens with build, right, you can see your PDB files here, right, or sorry, right here where it says PDB file with hydrogens. If you click that, that will download your PDB file that has the hydrogens added. Now, if you look at that file, so I have created a test folder here, and if we open up data, where we have all our data, and look at the PDB file, what you'll note is the hydrogens have now been added to your PDB file, right? So they'll be labeled H01, H02, H03, right? And this is what you will use to input for Sparta Plus. Now, if I go back to Sparta Plus's page, the input is quite straightforward. It's just Sparta Plus -in protein PDB. So if we go to the directory that contains the Sparta Plus file, or the PDB file, sorry. Right, so if I go here, and now I look, and what we want is Sparta Plus -in, and I've labeled this the modified new hydrogens added PDB. And if you click this, you will generate two files, a struct.tab and a pre.tab. And the pre.tab will look like this, and it will contain a number of different pieces of information. Here you have on your first column, your residue number. Second column is the residue ID that they call, so what type of amino acid it is, single letter abbreviation. This is the atom type. And then you have your chemical shifts here, right? So you have two different types of chemical shifts. I would recommend reading the paper here that accompanies Sparta Plus that can be found right here at the top for a more detailed explanation of what each of these parameters are. But these are your chemical shifts that are predicted, and this is the error of that prediction. So there are a number of different ways you can use this, right? For example, you can compare your assignments when you're done with this prediction file, right? But the question is, how do I use this to assist in assigning my protein? And for that, I have created a tool called PAL. So to get this tool, you can just go to my GitHub here, PAL, and click on it. Actually, this is the wrong one. Let's go to the repository. It's this one, PAL. And this is comprised of 5 different programs, and we'll cover the programs throughout this video. But to download, you can just click here and download zip. And then we have this PAL folder. So I want to take all of this and I want to extract it to a particular directory. So here I'll put it in test, where all my data is currently in. Extraction complete, close, close, oops, don't want to click that again. So if we go to this directory, now we have this PAL folder, and this contains the program. Now PAL is not actually built into NMR box yet, so we'll have to set up a virtual environment to get it working. And these are basically the instructions. It's quite straightforward. So if I go back here, and let me go one directory back, so now I'm in the directory that contains this PAL folder. To create a virtual environment, what I'll do is type in Python 3-m venv env, as you can see here. That will create a virtual environment folder with a label that's called env. So what you want to do next is then go into the activate your virtual environment, source env bin activate, and you will want to copy the PAL file here. You will want to copy these into this virtual environment that you have just created, right? So then you want to go into the env folder, and here you want to install all of these dependencies. So pip install --upgrade pip, and each of these will take a couple of seconds to install properly. And oops, once that's done, you want to do pip install -upgrade setup tools. And these are just to ensure that the program works properly. If you do not do this, the program will not work in NMR box properly. And then the last one is, I forgot to, we also want this requirements.txt in this virtual environment folder as well. Requirements.txt, do that as well. And this one will take a couple of seconds. And once that's done, what you can then do to run the program is just python 3 pal.py, right? And make sure, again, you're in the folder that contains this pal.py file. And now this is PAL. And like I said, there are a number of different programs built in. What we're going to use first is AVS. So let's discuss first the theory. What are we actually going to do? How are we going to use this, let me close this pre.tab file, and how are we going to use this to assist in our assignments? So what you want to do when you're doing your assignments normally is you're going to have a bunch of experiments that have chemical shifts for different atoms, right? So you're going to have HNCO that gives you your carbonyl chemical shift. You're going to have an HNCA that gives you your C alpha. You'll have an HNCCB that gives you your C beta. And the nitrogen, the amide nitrogen and amide hydrogen can come from your NHSQC. And maybe you'll run an HBHA-NH. So you might have your H alphas as well. And what you can do is what's known as calculating the RMSD between the experimental chemical shifts you have and the chemical shifts that are predicted in your Sparta Plus file, right? So what does that mean? That's basically this equation. And you can see there's a number of different ways to show it, but they all effectively, this is a really small image, but I hope you can see this here. It all is the same thing. Effectively, what you're looking at here is calculating the distance between 2 points, right? So for your nitrogen, this would be Xi would be your Sparta predicted chemical shift for the nitrogen. Y would be the experimental, so from your NHSQC, what you're seeing. Then you square that. They don't show it here, but you would divide that by the error that's in the Sparta plus file. You square that. And then you can add multiple atoms, right? So you do the exact same thing for your carbonyl, for your C alpha, for your C beta, and you add up all of those values. Then you divide it by the number of atoms you have, right? And that will give you, once you take the square root, the RMSD. Or in other words, how far or how much deviation do you have from what's predicted in Sparta plus from your experimental. Now you'll notice that this Sparta plus prediction has these 6 atoms predicted for every single amino acid, except for, of course, prolines. They don't have an amide hydrogen. And so in those cases, what you'll be doing is calculating the RMSD of your experimental chemical shifts with the predicted chemical shifts. So you're going to go through this entire table and in pairs of 6, calculate the RMSD of your predicted. So if this doesn't make sense, don't worry. I'll actually go through with how to use this tool, but this is the math that's going on underneath the program that I have written. So the first thing we have to do is actually reformat this pre.tab file to be able to do this. This has a lot of extra information we don't really care about, and I also don't care about any of this remark and extra stuff up top. So to do that, we're going to use this AVS program. And this is quite straightforward. All you really need to do is upload your Sparta Plus file. So if I go here to data, we generated that pre.tab file from Sparta Plus. And all you have to do is upload that and then indicate a save file. So this will be Sparta output text. Now, in many cases, you're not going to potentially be assigning the entire protein in your Sparta Plus file. Maybe you're assigning only a particular domain. Maybe you're assigning a little bit less, a particular part of that protein. So the Sparta Plus file may have extra information that you don't need. Additionally, you may have mutations, right, that deviate from your Sparta Plus file, from the PDB. So what you want to do as well is upload your sequence file, right? So I have a sequence file here, and it should be important to note that the format of this sequence file, if I go here and I open up the sequence file, yeah, it's over here. It should be single letter abbreviation, and it should be just one single line. So no spaces and no line breaks. And what you also want to do, again, if you have any mutations here, you can input them. But what you also want to do is put in the amino acid number, right? So in your sequence that we have here, what is the very first amino acid's number within the sequence, right? So this methionine that we have here, is this number 1? Is this number 2? And the numbering has to be identical to the PDB. So if you're, for example, working on a domain that's near the C terminus, and this methionine is in fact amino acid 200 in the PDB file, what you would put here is 200. In our case, it's just the very first amino acid. So we click enter, and then we click generate Sparta file only, right? So this will generate this Sparta out.txt file. And if we open this, we can see that all of that extra information we saw earlier is gone. And now you have a single file with 1, 2, 3, 4, 5 columns. First column, again, amino acid residue number, residue type, atom type, your chemical shift that's predicted, and the error. And this will be the size of your sequence, right? So if you have, if your sequence is smaller than Sparta Plus file because you're only assigning a particular portion, all of that extra stuff will be chopped off, right? So if we close this, actually something that might be important to note, you'll note that in some cases, you'll see extra values added in. For example, prolines don't have amide hydrogens. And you'll see it'll be given a value of 1,000. This is important and crucial for how the program works because the APS program, which we will cover next, goes in blocks of 6, and therefore all amino acids need to have 6 values that are predicted. And this is why prolines are given these amide hydrogen values, so they also have 6. And something else to note, the ends, the very first amino acid and last amino acid, also will be chopped off because those don't have 6 when they're first predicted in Sparta Plus. So we're going to exit out of this, and we're done using AVS here. So we'll just minimize this for now. And what we want to use now is APS. This is what will be used for your predictions. So you can see the first line here for APS is your Sparta file. This is what you generated with APS. So what you want to do here is, if I go back to data, we labeled our output file as Sparta_out.txt. So you want to upload that here. Now you'll see it says a chemical shift file, right? So to explain what that is, let's walk through your data first, right? So say you have this setup, right? You have your HSQC, your HNCA, HNCACB. Here we have an HNCOCA, an HNCO, an HNCACO, and a NOSI, right? So let's say you go to a particular peak here, right? Say none of these are assigned and you have this amino acid here, right? And you look at the C alphas in your HNCA, you look at your C betas. Let me bring these down. And you notice, oh, I have two alanines back to back, right? An I and an I minus 1. But where in your sequence are these alanines? And maybe you have multiple pairs of alanines, right? Which one of these pairs is it? Right? So that's where you can use this Sparta Plus, this APS program, right? So what you do is you create an open text file. So let's say here, right? And let me get rid of all of this. And you input your chemical shift values starting from the I minus 1 going forward, right? So the very first entry here is going to be what you suspect to be the I minus 1 values, right? So we don't have a nitrogen value for that I minus 1, right? And so it should be important to note that the format should be nitrogen, the alpha hydrogen, the carbonyl carbon, the alpha carbon, the beta carbon, and the amide hydrogen, right? So what do I mean by that? So we don't have an amide nitrogen, so we put 1000.00 as a placeholder. It's absolutely important that everything is a decimal. So you have to put 0.0 somewhere within your numbers. We don't have an H alpha either. So we put 1000.00. We do have a carbonyl value from our HNCO. So if we go here and we look at it, it's about 179.3. So we'll put 179.3. We do have a C alpha value, I minus 1. It's 55.15. We have a C beta But in this case, if these aren't assigned, we won't know which one of these is actually the C beta, so we'll just choose the average, 17.75. And finally, we don't have an amide hydrogen, so that'll be 1000.0. So that's the I-1. Now we also contain information about the I. So let's put that in as well. So for that, we have the amide nitrogen, which is 117. We'll say 0.0. We don't have H alphas here. We do have a I carbonyl. We do have the carbonyl value from the HNCaCO. So that's 179.4, 9.4. We do have an IC alpha, 54.4. And again, we don't know which one of these two is the I and which one's the I-1, so we'll pick the average of the two. And finally, the amide hydrogen, 7.265, right? So let me get rid of this top portion, and we'll save this as the unknown. So if we go back to APS now, and we click Browse, we upload this unknown text that we just made, and we set an RMSD threshold. So what will happen here is this unknown, right? This, you'll notice, is in pairs of 6. And what it will do is calculate the RMSD difference of these two amino acids that we have here, these two pairs of 6. Let me bring this side by side. So this will calculate it, the RMSD, with each pair here. So for example, what the program will do first is you have this phenylalanine 11 and this glycine 12. So the RMSD of these two amino acids will be calculated against this phenylalanine and glycine. Then you'll calculate the RMSD again of your unknown with the glycine and this glutamate 13. And you do this for every single pairs of 2. Now, if you have 3, it'll be calculated with pairs of 3, and you'll get an RMSD for every single pair. So let's run the calculation first, right? This RMSD threshold basically sets a filter. It only shows you those pairs of RMSD matches that had an RMSD below the value you put. So let's put 3 for now and click Enter. And there are 2 different ways of calculating this. We're going to use the way I just discussed, where you just take the entire text file that you have and compare it to pairs of matches in the Sparta Plus file, and click RMSD sum. So let's first look at the text output. So you have a number of matches, right? Again, these are pairs of 2 that are matched with your Sparta Plus file. And this is sorted from lowest RMSD to highest, right? So generally, the lower the RMSD, the closer that your values will be to your experimental values will be to what's predicted, right? So you'll see here, leucine 122 and leucine 123 are one of your matches. We know that's not the case since we know both the I and I-1 are alanines. Here you have alanine 16 and aspartic acid 17. Again, that's not the case. And if we go through, we'll notice we only have one alanine pair, 124 and 125, that matches these values. And if you look throughout, there's not really any other alanine pair, right? So this immediately tells you in your amino acid which pair this is. And on the left here, I've also, it'll generate a plot that shows you exactly the same thing here. And if you click on these peaks, it will highlight which amino acid pair this is looking at. But you may have noticed that this alanine that we have here, right, this alanine pair, its RMSD is not the lowest. There are other stuff Sparta predicts that match as well. And this underlies a fundamental problem in terms of the limit of information that you can provide it. 2 is generally not enough, unfortunately. you have to have, I'd say, a minimum of 3 to get a pretty accurate pair that you're confident in. So what I mean by that is, let's find the I+1 of this alanine, right? So say you come here and you have your strip plot, and you use this strip plot, and you get your HNCACB, or sorry, your HNCA, and well, there's a lot of matches, but I'm sure if you run a strip plot with your HNCB, you'll get a singular match, right? And if we go here to its I+1, which is phenylalanine 126, right? Now, where's the one we had open? Right here. Now, when you're working, it won't be assigned. It'll just be another unknown, right? So what you can do here now is you input the values here in the same format. So first the nitrogen, 117.5, right? Then you want to put the alpha hydrogen, which we don't have, so it's 1,000. Then the carbonyl, which comes from the HNCACO, so 178.0. The C alpha, which in this case is 61.95. Your C beta, which here will be 39.2. And finally, the amide hydrogen, 7.977, right? So again, this is the I-2, I-1, I, right? So this is the order that they have to go in. And we'll click Save. And now if we go back to APS, right? And we clear what we had run, and we run it again. Now with 3 amino acids, you can see that the distinction is far more clear. The very first one that you get with an RMSD of 1.54 is this alanine to phenylalanine, right? The next one that you get is 2.1. So this is quite a bit higher. This can become more apparent if you look at this plot below, or to the left as well, right? You can clearly see there's one match that fits better by quite a bit than all of the other matches. Generally, I find RMSD below 2 is a good fit. If you have an RMSD above 2 or 3, then it's probably an erroneous match, and you should not assign your protein using the Sparta predictions that you have obtained. But let's show how good this match and this pairing system is when you have more than 3. The more atoms you put in, the more information, in other words, you put in, the better and better the match you're going to get. So say you find the I+1 of this, right? You run another strip plot, and you find the I+1 of this amino acid, right? So here we, again, continue the cycle. Nitrogen value first, 119.3. The alpha hydrogen we don't have, so we put 1,000. The carbonyl value we have at 178.8. The alpha hydrogen here is 62.1. The beta hydrogen is 34.55. And finally, the amide hydrogen is 7.57. So let's save this and, oh, wrong one, sorry. And clear this and run it again. Now you can see that this distinction and deviation is even more, right? We've gone from, I think, the previous 5 or 6 matches now to only 4. And this difference between the two is even larger. And in fact, if I change this to 5, you can see from the plot at least how obvious your match can be, right? It's quite clear from all of these amino acids. There is one that matches far better than all the others. And this is the strength of this tool, right? This allows you to basically search your sequence list and your Sparta Plus file and use those predictions to find the best match that you can get to assign your protein. So if you were assigning the protein normally, I think this is a good enough match with the data that you have to assign the section. And now you know that this is amino acid 124 through 127, right? So this would be amino acid 124. This would be amino acid 125. This would be that phenylalanine 126. And this would be isoleucine 127, right? So this can be used in this manner to assist in your assignments. But we can take it actually one step further as well. So let's say you have a scenario, right? You run a strip plot to determine where the I+1 of this amino acid is, right? You don't have it assigned, you don't know. And when you click your match in your strip plot, let's get rid of this duplicate, you get 3 potential matches. And let's say you don't have any extra info. You don't have your HNCAs, you don't have carbonyls. You don't know, you can't differentiate it and identify which one of these is actually the I+1. Sparta Plus can be very useful here, right? So let's go to this match, this very first match here, right? So if I type in LT, and that's this peak here, right? So if we take its information, right, and we put it in, so that's this guy here, 117.5 and 7.977, and we click run, right, we'll see that this 124 to 126, right, this matches, because in our sequence, when we look at alanine pairs, 124 and 125 is an alanine pair. The rest of these, none of them, as you can see, start with an alanine. We can ignore it. So we go, okay, this amino acid, phenylalanine, or this amino acid at 117.5 and 7.97, and our strip plot that we got, this is a good match. This fits the data that we would expect. And it has an RMSD of 1.54, right? So let's go to the next match, right? If we go to this one right here, and let's input its information, right? So say this is 108, 108.7, right? And the C alpha is 175, 175.0. The C alpha here is 62.25. 62.25. C beta is 69.37. And finally, the proton is 7.56. Right? So we'll save that file. We'll go to APS and we'll run again. And now what we'll see is, let me clear the previous stuff. We'll see that that alanine-alanine match has completely come up here now to 2.41. And now this is saying the best fit is this aspartic acid to this valine. We know that's not true. We know that it should be an alanine-alanine pair, right? And we can see that the RMSD of that alanine-alanine pair, which suspected, which was 124, 125, it's now shot up to an RMSD of 2.41, right? So this strip here that gave us an RMSD of 1.54 is a much better match than this strip here that gave us 2.41. So we can use Sparta Plus in this way to actually get rid of this, right? So now we have this third strip, this third potential match. So we'll do the same thing with it, right? So if we go here, we will put in 120.6 for the amide, and for the carbonyl, we'll do 179.2, 79.2. The C alpha in this case is 53.85, 53.85. The C beta is 17, oh, sorry. Yeah. 17.73. And the proton value is 7.6. So we'll save, we'll run APS again. And now we can see that in our RMSDs, right, now we have that 124A to 126 is completely gone. Instead, it's replaced with this 122 leucine to 124 alanine, 123 leucine to 125 alanine, and a 133 to 135, right? So we know this also is in the match because we know our very first amino acid right here at the top, we know this is an alanine, not a leucine or a cysteine, right? So this third match as well can be eliminated since it does not match with the Sparta plus of what it should be. So all that leaves is this singular match here, right? This phenylalanine, which if you put in gives a good RMSD and matches with your previous one, right? So in this way, we not only used Sparta plus to assign this string of 3 amino acids, right? We also use Sparta plus to eliminate other strip plot options by calculating what would the RMSD be, right, if we included, or rather we replaced this value here with the results of the strip plot. And we saw that out of 3 options, only one of them gave a low RMSD that made sense with the other pieces of information that we had for our assignments. So this is another very useful way that you can use this APS to calculate or to assist in assigning your protein. Now, if you don't think this is pretty cool, I don't know what to tell you. But let's say you do think this is pretty cool, but you're thinking to yourself, oh, unfortunately, I don't actually have a structure for my protein. The structure has never been solved. So I can't use Sparta plus, so I can't use these really cool tools to help assign my protein. Well, what you can use, it's true, you can't use Sparta plus. But what you can use is the average chemical shift values of amino acids. So you'll notice in this PAL file, right? So if we go here and we go into the peak list assignment library, and you'll notice there's this file called test files, and you'll notice there's these AVS test files. If you open this up, there is this file called csstat_aa_full. And if we open this up, this is a list of every amino acid and its respective atoms, along with the average chemical shift. This comes from BMRB, by the way. So this is BMRB reported average chemical shifts for the atom for that amino acid and a standard deviation, right? So for example, alanines C alphas generally have an average chemical shift of 53, and that's plus or minus 2, right? So the range of chemical shift for alanine is 51 to 55, right, for C alpha. For C beta, it's 19 plus or minus 3, so the range there is 16 to 22, right? So we can do the exact same RMSD calculation, but using this table. So you can take this table, copy and paste it to that data file. That's what I've done here. So I have it here labeled as bmrb.csv. So again, this will need to be reformatted, and that can be done using AVS. So here what we'll do, instead of the pre.tab that was used for Sparta, we will replace it with that BMRB file. And here I'll change the save file now to bmrb output.txt. And instead of clicking generate a Sparta file, what we will do is generate a BMRB file, right? And again, it's incredibly crucial. Your sequence is indicated here, and this time mutations aren't relevant because this is no longer reading a PDB file. This will read your sequence file, and the amino acid start as well. That's incredibly important as well. So then you click Generate BMRB File Only, and this will generate this BMRB output. What this does is you'll notice it looks identical to the Sparta Plus file, right? So this Sparta out that we had open, you'll notice these two are basically formatted in the exact same way. What this does is it generates the same, you can think of it as a pseudo prediction, a pseudo Sparta file for using your sequence for every single amino acid. And these values and errors come from the BMRB average chemical shift database, right? And this works pretty well, similar to Sparta Plus, right? So the way we would use this is if we go back to APS, we'll change this Sparta.out now to the BMRB.out, right? And if we use the same format that we had here, so if we go to our unknown, right, and let's replace it with the correct match, right? Actually, let's go through this entire process again, right? So let me bring up the strip plot. Let me go back down just to show you how this can work just as well, even if the structure is not solved. Sorry, phenylalanine. Right, so 117.5, right, and then the HNCO, or the carbonyl value, I should say, 177.9. Your C alpha, 62.0, 62.01, we'll say. Phenylalanine is 39.19. And your amide hydrogen is 7.97. So let's save this. And now clear, run using armistice sum. Oops. Why are there? Oh, this must be from the old run. So a couple of things you'll notice right off the bat. Using the Sparta input, right, we ended up getting, I think it was 4 or 5 matches. Using the BMRB as a prediction file, you can see it's quite a bit less stringent, and so you can get a lot more matches, right? You get a whole table of matches. However, you'll notice that there is one match that stands out from all the rest, and that is that 124 to 126 phenylalanine, right? So while the BMRB approach is less stringent, if you have at least, again, 3 amino acids within a row, right, it can be used just like the Sparta Plus can. Actually, I still have the Sparta Plus open. Forgot about that, right? So you can see here that you actually get a much better fit to the BMRB than the Sparta, the BMRB gives a much better fit, an RMSD of 0.69 compared to the Sparta Plus. But the Sparta Plus only has 7 potential matches, whereas BMRB gives you a ton more. And when this becomes problematic is, say, you only have these 2. So let's clear, run armistice sum. And you can see using, again, 2, pretty good match, but now you have 2 pairs of alanines, 155 and 156. Or sorry, 155 and 124. And it's impossible using just this pair with BMRB to determine which one of the 2 it is. Whereas if we use the Sparta, right, and clear, you can see that the 124 here, you don't even see the other AA. You don't even see 155, right? So 124 actually shows up, whereas the 155 isn't. So using this pair, you're actually able to know which alanine-alanine pair this is in your sequence. Whereas using the BMRB, you can't really differentiate between the two, right? So that's some of the pros and cons. The Sparta Plus will always be the better approach because, some amino acids that might be outliers, that might have unique chemical shifts because of the structure, will show up very nicely in Sparta Plus, whereas in BMRB, they would actually have a higher RMSD and be difficult to assign because they are outside of the average normal ranges that you would get for those amino acids. So ideally, you would always want to use Sparta Plus, but if you can't, then this BMRB is better than nothing. And as you can see, if you have 3 or 4 amino acids in a row, you can use it identical to Sparta Plus. It's just as effective. So this is how you can use this APS program to use these Sparta Plus values or just the BMRB values to assist in assigning your protein. So let's now move on to the next program. So let's close this. Let's just close some of the stuff we have open right now. And we will close AVS. We'll come back to AVS later. And let's open up, let's close the strip plot, minimize this, and let's bring up PAL. So the next program that I want to talk about is the strip plot, right? Now you might be thinking, why would you want a strip plot? Sparky already has a strip plot built in. Well, Sparky's strip plot has some limitations, right? So take, for example, here we have an HNCA and a HNCA-CB that's C-beta optimized, which means the HNCA C-alphas and the HNCA-CB only has C-betas, as you can see here, right? If you search only the C-alphas or only the C-betas alone, you're going to get a lot of matches. What you would ideally want to do is search both the C-alphas and C-betas. Unfortunately, Sparky can only match and search one strip plot at a time, right? So if you click the HNCA and HNCA-CB and say you want to search this I-1 C alpha and I-1 C beta, and you click peek, right? And you click match, it won't work. You cannot search both the HNCA and HNCA-CB. Your only options here are either to just search the HNCA, which will get you 19 different matches, which is useless, or search the HNCA-CB using the C-beta, which will get you 4 different matches, and then you'll have to go through every single 4, right? You'll have to visit, 3 matches. You'll have to visit every single 3 and look at its C-alpha and make sure that fits, right? This is incredibly tedious and annoying. Additionally, say you want to run strip plots for your NOSI and HNCA. In many cases, maybe you don't have C-betas. And as I will show you, HNCA and NOSIs can actually be enough to assign your entire protein sometimes, depending on the quality of your data. But you can't do that in Sparky, because if we look at just the NOSI, if we look at the HNCA and the NOSI, so say you want this I-1 and you want, you want this I-1 and you want to match this NOSI as well, right? So you want to find a corresponding peak whose C-alpha matches what you have highlighted here in the HNCA and who has both of these peaks in the NOSI. Again, peak and match, it's just not going to work, right? So what I've done is made my own strip plot, and it works almost in an identical fashion to Sparky's strip plot. The only thing that is incredibly important to keep in mind is the nitrogen values that are associated in your 3D experiments must match the nitrogen value in your NHSQC. What I mean by that is if we go to this phenylalanine 126, Its nitrogen value is 117.481. This must be identical for every single peak in your 3D. So if we go to the alanine, or sorry, this peak right here, its nitrogen value is 117.481, right? This is good. These two must match. The same is true for all of your nosy peaks. They must all also have the same value as this, the nitrogen here, right? So you can see here that this has that. This is also 117.481. This is also 117.481, right? So this is how every single peak that you've picked should be. And if you're just picking peaks, right, they will be. As long as you never touch the peak here in the NHSQC, these will always have the same W1 dimension, right? That nitrogen dimension will always be the same. But if you ever use peak center, or if you move this peak, right? So say I move this ever so slightly to the left, now it's 117.49, and these peaks are 117.481, right? So these are different, and the strip plot will no longer work for them. So that is absolutely critical. They must be identical, right? So all you do is upload your peak lists. So let's go to the data, and we have our peak list here, the HNCACB. We have a, HNCA, we have an HNCACB. I won't upload HNCO and HNCOCAs for time's sake, but they work in the same fashion. You can also upload HNCOCA, and we'll do the nosy. We'll keep it simple. Where is the nosy peak list? Nosy. Oh, here it is. And then close. The carbon and hydrogen tolerance, if you go to your strip plot in Sparky, you'll notice they have a hydrogen carbon tolerance. I'd recommend using those parameters, so 0.2 and 0.02. And the reason this tolerance basically is what range of deviations will you allow, right? So if you have a smaller range of deviations for carbon or hydrogen, you're more likely to get the exact match that you're searching for, right? If you have a wider range, you're going to get more matches, right? 0.2 and 0.02 I find are pretty reasonable ranges. If your carbon value deviates by more than 0.2, it's probably not the same carbon that you're searching for here. So now you input your values. So for the C alpha, you do 54.4. For the C beta here, you would do 17.6. And this nitrogen value is incredibly important as well. So 117.481. So this program works on a filter system, and that's why this nitrogen is incredibly important. It will search each of these strips. It will locate peaks that have the same nitrogen value, and you will only have peaks that have the same nitrogen value that correspond to this amide. So this works well. This is one advantage this technique has over Sparky. You will not get peaks from poor resolution or slightly overlapping, because those peaks will have distinct nitrogen values, right? Sparky will give you matches even if you have poor resolution or overlapping residues, so you can actually get more matches than you would normally want because of this reason. So it's just a different way of doing things. So make sure you just click enter on all of them. So this program is set up in two ways. These first two columns that say backward, forward, and NOEs, these run the actual program, but they will not display anything. To display matches, you have to check mark this. So if I click C alpha only, this would be identical to, if I take the strip plot and I say only search the HNCA, and I pick this peak, right, with this C alpha value, this would be identical to this, right? But if I don't click display, it'll say the values using, and you'll notice there are no matches here. So if I want to see the matches, I have to click display carbon matches. and then click Run. So here you can see you get a bunch of matches. And you'll notice, if you ever compare them directly side by side, you will get the exact same matches that you get in your strip plot, right? Now there's also an option here to exclude nitrogen in the identity search, right? So what you'll notice is, in many cases, you will get the same match, right? You'll get the duplicate. Basically, Sparky has this as well. This is why when you run a strip plot, you get two instances of what you're searching for. So if you click this, run matches, right? This should eliminate that problem. But you'll see you get way too many matches if you run your C alpha, right? So what you can do is run your C alpha and C beta. So search both of them. And now you'll see that really you only get one match, right? You could not do this using Sparky. Say you don't have the C alpha, right? And you only have the C alpha and your NOEs, right? So if we click display NH matches, right? You'll get a bunch of C alpha hits and then you'll get some NOE hits down here. What's happening here is you're running your strip plot as you normally would, and you're getting all these matches from your HNCA. Then you're using your nosies, right, to filter. So the idea is, as we discussed in the previous video, you will have sharing NOE values, right? If this NOE is looking at its I-1, its I-1 will be able to see its I+1, right? So this filters this list of HNCA values with these nosy matches. So you went from this big list of matches, I think it's like 20, down to basically 3, right? Because you have this similar match, right? You can do the same thing with the HN or with the CACB, right? If you run that, you'll go down from, well, you'll basically have these 2 matches, right? So let's look at another peak just for an example, right? Let's go to this veiling here, right? And so far we've been looking at I-1. Say we want to go to the I+1. So the first thing we'll need is its nitrogen value, 118.298. And then we'll need the C alpha of the I, 62.8. And the beta, which here is 32.33. Right. So click enter here, and we'll run just the C alpha for now. So running just the C alpha, you get 4 potential matches. Let's see if we get any from C alpha. Here we go. Running the NOE filter, right? So looking at your nosy matches as well, you went from 4 to 3. So you're able to eliminate 1. Let's run a C alpha C beta. So running just the C alpha gives you 4. Running the C alpha C beta gives you the same 4. But running the nosy, so this again is sequential, right? So running the nosy filtering the CACB now only gives you 2, right? And you can see how well this works, right? Since this is assigned, if we go to its I+1, you'll notice that its nitrogen value is 122.24. And that's exactly the match that we get here, right? So this can be I think, powerful tool for combining your HNCO, HNCACOs with your nosies and your C alpha and your C betas. So instead of Sparky that you can only search one experiment, one triple resonance experiment at a time, this strip plot allows you to search multiple. You can also go forward by looking at HNCOCAs, right? So even though we're searching for the I+1 here, you'll notice I had selected the C alpha only and C alpha C beta in the backwards. This is because HNCAs and HNCACBs show you both I-1s and I's, right? So you can go forward and backwards with them. The nomenclature here, so this says CACO, right? So what this would be is starting with the HNCA, and then using the HNCO, the HNCACO as a filter, right? So you would enter a carbonyl value here. So in this case, say we want to go backwards, right? So we would click 177.4. And we would click this CACO. What this would do was then search your H and CACO for this match, right? Since you're looking for the I in that case, right? The CACBCO would first run a strip plot on the H and CA, then filter the matches you get there by running another strip plot on the H and CACB, then filter those matches by running another strip plot on your HN CACO. Going forward, same thing, right? So you can search just the HN CACO. You can search the CACO. So what this does is run an HNCA first. Then it will look at your HNCO, right? And I think the rest is pretty self-explanatory. Don't want to go too into detail, but the README will describe this in more detail. Just want to say this is exactly like a strip plot, except here, instead of clicking what you want to search, this is more sequential. So here you do the same thing. I want to search the HNCA, or I want to only search HNCACB, right? Or here I want to search the HNCA and HNCOCA. So it's just different triple resonance experiments that you'll be searching through. Now you'll notice for NOEs there are two options. There's the NH, which is quite self-explanatory. This searches the amides that you have, so it searches between a region of 6 ppm and 12 ppm for matches. But there's also an H-alpha option, right? So sometimes your H-alphas will also be shared, right? The amides are going to be close to the H-alphas for your I and I-1s. This is a deuterated sample, so there are, I don't know why this is not working, but as you can see, there are no H-alphas here. Okay, now it works. There are no H-alphas since it's deuterated. There are only amides. But in your protonated sample, if you have a lot of NOE P matches for your NH groups, you may want to run this HA-NOE as well. And then you can display this right here, combined NOEs. What this does is this only shows matches that are shared, both among the amide matches and the alpha hydrogen matches, right? So this is just another further filtration step. Now, there is one additional tool built in here, and that's this identify option, right? To be able to use this, you must have in the file, if I can find right here, the file that contains the peak list that you just loaded up into this program must contain this bmrb.csv file, right? And this is, as we saw earlier, just a list of the average values, the average chemical shift values for each amino acid in atom, right? And what this does is this looks at the C alpha, C beta, carbonyl, nitrogen, and amide hydrogen value if you want to include it as well. And it will give you based off the average chemical shift values, what it thinks the amino acid type you're looking at is, right? So actually, let's close this. So take this valine here, right? An amino acid with a C alpha at 62.8 and 32.14, right? Now, we had discussed earlier about a table that you can actually use to determine what type of amino acid you have, right? So you can use this table here to determine what you're looking at. The problem is, as you can see, this might take a bit of time, and sometimes you get multiple matches and you have to go through it. It's just a lot to look at. Instead, you can have a program just read through the table and give you a printout. So if you click identify, right, according to this at 62.8 and 32.33, right, with this nitrogen value, this correlates with a proline. And the reason that it doesn't correlate with a valine is because the range of tolerance is pretty small to begin with, right? So if you are not in the exact range and standard deviation that is in the BMRB deposited files, you sometimes will get erroneous matches here. So there's this option that says identify tolerance, right? And this allows you to increase the tolerance range. So if I click 1.2, this would increase that tolerance by 20%. So now it'll tell you identity tolerance has increased by 20%, and you can see that you get both a proline and a tryptophan that could have these two values. Still don't get a valine. Now this might be because of the nitrogen value. So let's get rid of this and see what we get. Now we see if we get rid of that nitrogen value, you can get tryptophans, prolines, valines. Tryptophans, prolines, and valines, right? You get these 3 additional options here, right? So sometimes you may want to play around with this, get rid of the nitrogen value because maybe it doesn't fit well. Most of these ranges, as you saw in this table, if I can bring it up, these are C alpha, C betas. Nitrogens, protons, and carbonyls can have a wide range, so they're not entirely useful when it comes for identity matches. So I'd recommend when you're looking at the identity of what you might have, just use the C alpha, C beta. So with your strip plots and with your identifier, it should be relatively simple to go through and find out, what type of amino acids you have for your strip plots, right? So say here, we want to know, I have this amino acid, C alpha at 57.2 and 31.8, right? What could that be? So if we put 57.2 and 31.8, right? And make sure you click enter. And I click identify. Oh, whoops, sorry, let me get rid of this C. I click identify. You can see you get a number of potential matches, right? So it could be an arginine, cysteine, glutamine, glutamic acid, histidine, lysine, methionine, or tryptophan. So this basically removes the need to look at tables like this anymore, right? You have now a list that can show you immediately what you have. And now we have an I-1. What could that be, right? So you can look at 51.8, and you look at a C beta of 28.6, 8.6, right? And if we click identity here, sorry, NMR box is being a little slow today. If we look at here, oh, sorry, let me get rid of this. Did I click enter for both? Oh, interesting. There are, 51.8, sorry, 58.1. I got these a little confused. Forgot to click enter. So now you can see you have an arginine, cysteine, glutamine, glutamic acid, histidine, tryptophan, right? So you have the exact same thing as last time except for a lysine, right? So now you can use this combined with APS. So just very briefly, just to show you what I mean here, let's just very briefly bring up APS. Just so you can see the power of using these tools in combination. And we need to upload our Sparta Plus file. So Sparta out. And let's modify our unknown text file here. Oh, I still have it open. Okay. So let's upload it with the information that we got from here. Right, so first you start with the I-1, so C alpha at 58.2, and reload, okay, 58 point, why can't I move this, sorry. Okay, now let's see if I can modify this. Yes, 58.2 for the C alpha. The C beta is 28.6. And we don't have the, let's say we don't have the I+1 matches for any of these, so we don't know the I-1, so we don't have nitrogen or hydrogen values for the amide. And we can see here an I-1 of 178.8. 8.8. Now we'll change this next one, 118.0. Again, keep in mind decimal places are a requirement. 7.611, and then the C alpha is 57.24. 24. The C beta is 32.0. And the carbonyl is 176.6, right? So let's save this. Let's look at PAL. APS. And then open the unknown. We'll put an RMSD of 3 here and run using an RMSD sum. As would be expected, right, because this is only 2 pairs, you're going to get a lot of matches. But now we can use the identifier, right, that we have here with this. So as we stated earlier, right, we know we're going to have basically this list followed by the exact same list. So the I-1, I+1 must contain, both of them must be an arginine, cysteine, glutamine, glutamic acid, histidine, tryptophan, or lysine. So we can see our very first match, 76 to 77. That's good. That makes sense. 69 to 70, right? So you have a histidine and a cysteine. That also matches what we have here. This glycine to cysteine doesn't. The sulfur to cysteine to, or serine to histidine doesn't, right? So using this, you can immediately start to cross out some of these alternative potential options that you could have, right? And again, this is also why I would highly recommend against just using Sparta Plus for your assignments. For only using 2 amino acid chemical shifts for your assignments. Because as you can see, this is actually 162. And well, if you look here, we don't even really have lysine 162 here, right? So this sort of shows why you need more than just the 2 that you have. But this can be a very useful tool just with this identifier. And you can use this strip plot. So let's say we've gone through 2 and we have so many matches, it's not definitive. So let's use the strip plot to see if we can find the I-1 of this amino acid so we can add more information to our table, right? So you're going to want to put in the nitrogen value here, so 118.05, and this nitrogen value must be exact, right? The C alpha and C betas don't actually have to be exact. And we'll put in 58.22. And for the C beta, we'll put in 28.62. And then carbon tolerance of 0.2. So let's just enter all of these, and we'll just use the CAC beta. That should hopefully only give us 1 match. Oh, okay. It gives us 2 potential matches. I wonder if we can narrow that down with the NOEs. Let me clear. Yes, so we can narrow these 2 potential matches with the NOEs, right? So if you look here, since this has been assigned, the NOE matches quite nicely. So 117.416. So we go here, and now we immediately have the nitrogen-hydrogen values for our APS. So if we go to our unknown text here, we can fill these in now. Right, so this is 117.4. So instead of 1,000, 117.4. And the nitrogen, or sorry, the hydrogen is 8.141. But now we have a new I-1 with extra information. So let's bring these down and come up and put, we don't have the nitrogen or the C alpha, But we do have the carbonyl. So let's move this here. So this is 177.4. 177.4. C alpha is 57.3. C beta is 31.38. 38. And then we do not have a amide hydrogen value for this. So let's click save, go to, APS again, and we'll minimize this. And let's run it again. So now we have this 90 to 92, 151 to 162, and a couple of other matches as well, right? This is probably a typo, sorry. This should be probably 161. But we know that the first two must be, or sorry, the last two, right? This amino acid here must be part of this list, right? And so you keep using the strip plot going backwards and backwards to search for your potential matches, right? So using these tools together can be really powerful, both for adding more pieces of info to this file so that you can run APS and find out, what the assignment is, as well as using this identifier to find out what type of amino acid. So this right here that we've now are looking at, or sorry, we can clear the identity and we can find out what kind of amino acid it is, right? So both of these can be very useful as you go through for assigning your protein. It just helps accelerate the process and make it easier, right? As you saw how easily we were able to find the I-1 once we were able to use the C alpha, C beta, and NOE values, right? So strip plot can be, I think, quite a useful, important tool. So let's look at another tool in PAL. So let's close everything and bring PAL up. This time we're going to look at the anchor point finder. Now it should be noted this says it's in beta because this doesn't always work. It's a little finicky. What this does is this tool looks for and finds amino acids, right? So these peaks here, that have both C alpha and C beta I-1s and I's, right? These are often really good starting points, right? Normally you look at alanines, serines, threonines, and glycines, and you try and use those at anchor points to do your sequential assignment. But once you've used all of them, which ones do you use now, right? Where do you start? And you want to start with data that you can create a string with, right? So even if it's a lysine, for example, or a glutamate, that are usually not good anchor points, if they have good quality data and you can link 2 or 3 amino acids, we've just seen how using that strip plot tool that I have, along with APS, using Sparta, how you can use these anchor points to assign your protein. So there are 2 parts to this anchor point. First, you want to upload all of your peak lists. And the same rule applies here as it did with the strip plot. All of your nitrogen values in your 3D, your triple resonance experiments, must be the exact same nitrogen value as is in the NHSQC, right? So let's upload the HSQC, the HNCA, and we'll just do the HNCACB for now, right? We only care about peaks that have these 2. The carbon tolerance, again, we'll put 0.2. And we're using a C beta optimized HNCACB, right? So that's important to just keep in mind. If you're using a traditional HNCACB where the C alpha shows up, do not check this box, right? So if you click here, run without matches, what will end up happening is a file will be generated. So if I go to data, you'll notice this file I and I-1 matches only. So let me bring this here. This creates a list of peaks that have both I and I minus 1s, right? And then it'll give you the label that you have assigned to those peaks, right? This can be very useful when you're first starting out. So these would all be good anchor points because they both have I and I minus 1 C alphas, right? So you can easily use a strip plot for these. And if you can find even the I minus 1 or I plus 1 of any of these, because you have C alpha C betas, that's enough with Sparta to assign them. So that's one useful way to use it. Another way would be if you've already, in this case, for example, assigned a good portion of the protein. And now, out of the unassigned peaks, you want to know which ones are good anchor points, right? So you can see there are some here that aren't assigned, and these both, so let's actually go to them just to show you what I mean here. So let's go to 115.827. All right, so if we go to this one here, we can see in the CA, CB, right? Or sorry, the HNCA, you have 2 peaks, right? 2 C alpha peaks, and you have 2 C beta peaks, right? You have 2 C beta peaks as well. So this is a good tool if you've either starting your assignment and have used up all your glycines and your serines and threonines and are looking for additional anchor points, or you've already assigned a portion of your protein and now you want to see, okay, what's left? Where else can I start? There is another way to use this tool as well, though. And you'll notice here it says run with matches. So you just saw you had this huge list, right? And the goal is to use those as anchor points to find I minus 1s or I plus 1s. Because if you have 3 peaks, or 3 amino acids, that's enough to use Sparta to try and assign them. So what this run with matches does is it runs strip plots through your HNCA and HNCA-CB. And it looks at and gives you peaks that have matches, right? So it'll filter, let me bring this up again. It'll filter this table and only show you peaks that have both I minus 1 and I plus 1 matches, right? So they're good anchor points that you know you can definitively branch off of to do sequential assignment. If you're going to run with matches, you will want to filter the C beta. So what that means is you won't want to include, right, your own C beta when you're searching, right? You will want to actually get rid of that because otherwise you're going to have more than 4. So here, I'd say 0.2 is a good C beta tolerance as well. So just make sure you click the filter C beta and then run with your matches. So you'll notice this will take a couple seconds longer because it has to run that strip plot. It'll give you this CSV output file, right? And this is not a text file anymore, it's a CSV file. And so you'll have your label as before, and you'll have the nitrogen peak, so that's the peak you're looking at. Now in this case, this program that's using a strip plot, it does not differentiate which is the I and which is the I minus 1. So it in fact will run all 4 combinations, right? So for example, if we look at, let's pick a random amino acid. If we look at this alanine, right, at 121.321, let me actually zoom in. There we go. We look at this alanine, and it has a C alpha C beta at 57.4 and 39.77, right? And so this can match in the strip plot using, these are actually, sorry, they should be here. So using the strip plot, it only finds one match using this C alpha C beta, and that's some peak at 119.127. But if you use 57.451 and the second BC beta at 31, you get these 2 other matches, right? The same is true if you go at 65.3 and 31.1. You will get 2 other matches, right? So this does not identify and try and figure out which one of your C alpha, C betas is the I or I minus 1. It runs strip plots on all of them, and the user can easily just say, you know, oh, let me open this. Why did this happen? Okay. Wow, that's really annoying. Sorry, NMR box is being a bit difficult today. Let's go to, oh, the whole thing is frozen. And hopefully it won't crash. So if we go to the peak, that's at 121.321. Click that, you will see it leads to this Valiant 18. And you can see why now this program's in beta, because this matched the label to the wrong thing. However, what you'll note is, you know, while this label's wrong, these matches aren't wrong, right? These are, you have two peaks. Why is NMR box so slow? You have two peaks. One at 65.316, the C alpha here, and one here at 57.45, right? And your two C betas, one at around 39 and 31, right? So this strip plot will show you both the I minus 1 and I plus 1 matches, right? So in this case, we'll see that the I minus 1 is 57 and 39, right? So this pair here at 57 and 31, we can delete this. This is the wrong pair. And the C alpha is, for the I is 65 and 39, or sorry, 31, right? Which we can see here. So right off the bat, say you want to use this as an anchor point, and this program has shown you that it has I minus 1 and I plus 1 matches. And in fact, it has already given you the values for those. So if we look at this amino acid that's assigned, you'll see that at 119.197, that is actually its I minus 1. And if you look here at the 65.3 and 31.12, which would show you the I plus 1 match here, we can see that we have 119.705, which corresponds to the I plus 1, right? So this, again, accelerates the process for assignment. This can immediately show you the anchor points. And, you know, this is a good peak to start with to try your assignments, since you have both I minus 1 and I plus 1 matches. So you not only have 2 amino acids, you have 4. And you can directly input those 4 into Sparta and should be able to just do your assignment right off the bat. So this again just helps accelerate the process. It gives you nice matches and good starting points so you can rapidly go in, get those values, plug them into Sparta Plus, or if you want to expand, right, the information that you have for Sparta Plus, you can use the strip plot tool and rapidly find additional matches for I plus 2, I plus 3, I minus 2s, I minus 3s, and put those into Sparta Plus and assign your protein. So just another tool that can help you with your assignments. But as you've seen, there should be some double checking. This program is in beta. There are, as you can see, a few problems here and there with how it functions. But the base core functions quite well. So this is taking quite a bit longer than I thought it would. So I'm going to split this up into 2 sections. So this will be, we'll say, the end of part A of this 3rd section. And then in the next section, part B, I will discuss the other 2 programs, the NOE distance calculator, which will be useful for backbone and side chains when it comes to using the NOEs to see what you should see within a particular distance. And going back to AVS, which its real purpose is not just for generating Sparta and BMRB files, but for actually reformatting your peak lists for BMRB deposition, running Talos, and for verifying your assignments using Sparta Plus. So we will cover all that in the next video.